Hello, everyone. Welcome to my session. My name is Samuel Baruffi, and I'm a pretty simple solutions architect with AWS. Today, I'm going to be presenting about Amazon Aurora DS SQL, which is a new relation database offering on AWS. So let's start talking a little bit about some of the current relation data challenges, right? We can give an example about running a Postgres database in whatever service or platform. It could be on your own EC2, could be on your on-premise, or potentially could be on RDS as a service as well. Some of the challenges that we have is scalability, right? Traditional databases have the capacity limitations that you would have an instance, and that instance, that server is your limitation. So customers would be constrained by these capacity limits of these traditional databases. And it becomes very hard to right size your application for the specific server that you might need to configure when you're provisioning this specific instance. Also availability, because it's a challenge, because now if you have only one server and that server goes down, we have lower resiliency that could potentially lead into unplanned downtimes, and it could impact your database availability. Of course, there are ways that you can have read-only replicas, and you can potentially help alleviate some of those concerns, but those are not very easy to manage, and there are a lot of pros and cons about that, right? So those are the functional challenges. When you look at the operational challenges, one of the things that is very common, and I keep hearing from many customers, is infrastructure management, like patching, upgrades, requiring a lot of engineering time to prepare potentially the database, prepare the server, test those. And that is a lot of engineering effort that goes just to keep your database up and running. Also is the complexity, right? Now you have a lot of infrastructure. You need to make sure you're installing the operating system, you're installing the database like the Postgres, you're part of that. You're doing a lot of fine-tuning configuration, which that not only requires engineering effort, but also require expertise that becomes very challenging. So with some, if not all of these challenges in mind, AWS have announced in December of 2024 during reInvent Amazon Aurora DS SQL, which is a cloud-native, serverless, distributed SQL database with virtually unlimited scalability and the highest availability of AWS. On this talk, we're going to talk about how that was possible, all the behind the scenes important architecture decisions that were made in order to make this available. So you have virtually unlimited scaling. That is one of the core concepts of Aurora DS SQL, because you have the compute and multiple steps of the compute that are independently managed and scaled. You can have writes and reads also being scaled separately, and both will be up and down as you need it, right? That allows you to have a business continuity, because you can now have a active multi-region distributed relation database on AWS that is completely managed for you. And you're going to spend a lot of time on the talk today explaining how that actually works. How does it mean? Because we know with traditional relation databases, actually with all the relation databases, there is a lot of locking issues, and how do you make sure the consistency across different replicas in different regions? How does that work? Another aspect that has been designed from the beginning is serverless. There is no server to provision. There is no server to patch. There is no software need to install or maintain or operate. It's completely serverless. And fast and easy is the idea of Aurora DS SQL is very inspired on other offerings on the AWS ecosystem and for serverless. So I'll give an example. If you create a DynaDB table, you just create a DynaDB table and you can start querying and actually insert data on that. The same idea is trying to be replicated here on Aurora DS SQL, which it should be very quick if you have familiarity with Postgres, because Aurora DS SQL is a Postgres compliant database where you can run some of the capabilities of Postgres. If you're interested in some of the capabilities and limitations, please check our documentation. But let's dive into the first way you can run Aurora DS SQL. So the first one is you can run Aurora DS SQL on a single region cluster. If you do not have the necessity to running active multi-region applications, because those can be expensive and not every single application requires you to have a active solution. So if you're okay, as you've been running potentially other traditional databases on a single region, you can create the SQL on a single region. By default, of course, because this is a managed offering on AWS, when you create a single region cluster, you operate it active across 3 availability zones always, right? So you can see you have your VPC with your application. You're going to receive an endpoint for that specific database. You're going to use that endpoint both for reads and writes. The compute, the transaction logs, which you're going to talk about in the future of this presentation, the storage, are actually replicated independently across 3 availability zones. This provides a 99.99% of availability, and all the transactions are fast and local, and also maintain ACID properties of your database. The transaction commits goes across availability zones, ensure data transactions are durable, isolated, and atomic. Of course, trying to maintain the ACID property. So this is the single region cluster that it creates. You have an option if you want a single region cluster or if you want a multi-region cluster. If you're going to the multi-region cluster, now Aurora DS SQL delivers 5 nines of availability across multiple regions. And the way this works, it's very unique and very interesting. So multi-region clusters provide 2 regional endpoints. And on this scenario, we are talking about a linked region. The way it works is you go on your AWS console or use the CLI or the API. You can create an Aurora DS SQL and you can say, I want a secondary region as a linked region. So in this example, you can see that we have 3 regions here into this architecture. We have region 1, region 2, where each region is going to have its own unique endpoint. So we're going to talk about how reads and writes work, but the good thing about having a endpoint per region is all the reads that are going to be done in that specific region using that specific endpoint are always going to be locally. You don't need to go across region. And that's one of the main benefits of the SQL. But also, writes are going to be synchronous, getting replicated across regions at the time of commit. We're going to explain what that means in a moment. The regions are equal peers. There is no leader or master node in this situation. And because you have this synchronous replication between regions, you always have a RPO of 0, which is really important for mission-critical applications. Now you see here that we have also a witness region. So the witness region is just replicating the journal. So we'll call that journal, but that is where the transaction logs of your database are. And in case of a failure, we're going to explain in the end of the presentation. In the case of failure of one specific region, you always are gonna have a quorum because this third region, which is the witness region. But on the witness region, you do not have an endpoint. It's just a witness region that is there to actually replicate it at the transaction log for the quorum. So you have always 3 up and running. So let's talk a little bit about the components of this SQL. So if we think about the components of the SQL is, you have the front end. So the front end, you can think about the endpoint on each specific region that you're going to talk to. Of course, that front end is being served to you across multiple load balancers that are replicated across multiple availability zones. But the interesting part here comes with query processor. So the query processors are responsible for executing the customer SQL, returning data in response to reads, buffering data in response to writes, and running the transaction protocol. So that's where Postgres will be running. Then we have adjudicators. Adjudicators are responsible for deciding whether a transaction can be commit while following isolation rules. We're going to explain how isolation rules work in a moment. For working with the journal in order for the transaction to actually be committed into the storage. Everything you see here from the adjudicator to the crossbar are only going to be necessary if you're doing a write, right? If you're doing a transaction that requires a write. The journal are an ordered data stream that makes transactions durable and replicated data between regions and availability zones. The crossbar is just a way that it can replicate your data into the storage. And of course, the storage, where is the data is going to be completely replicated across different storage partitions. And this SQL takes a very interesting approach of replicating the different pieces of data across different storage. So you have the replication and the performance capability benefit given to you by default. You don't need to you don't see any of these components here. We're just talking about these components so you have an idea how it actually works. So let's talk a little bit about how different transactions, like a read transaction, a write transaction, operate, so you understand how these components, which potentially by now are still a little bit confusing, but how these components will be put in place and how do they work together. So if we look here, let's just try to illustrate how it all works together. So we reduce the complexity. We'll follow a transaction from end to end. We're going to start with a read transaction and a base select statement. Let's imagine that a user is on a specific region, US is 1, and that user is looking to order pizza from a local restaurant in, let's say, Virginia, right? So what happens there is the user decides what food he wants from the restaurant based on a specific rating. So in this case, let's select all the restaurants where ratings equals to 4. What happens behind the scenes at this from this point? Because you've done a select statement, which is a read statement. How does DSQL manage that statement? So let's look into that. So you have the client who connects to the front end. That means a specific regional endpoint. This could be a multi-region linked cluster, or it could be a single region. For the examples you're going to provide today, let's say they are all multi-region. So when you do this specific request, that request will go to a load balance on the front end, and then we'll create a query processor, which where your transaction will actually happen. The query processor will actually use a start time, and this is one of the very unique benefits and capabilities of DSQL and AWS is this time that is being retrieved from the local clock is using what we call the Amazon Time Sync service, which AWS uses highly accurate global standard time by leveraging satellite GPS signals alongside with atomic clocks references, which is crucial to ensuring that time in one region and time in another region are actually aligned, because speed of light and how clocks are aligned can be problematic if you're not using atomic clock and you have satellite communications to pinpoint that, right? So when a query gets processed by the query processor, we have time at the stop, which is a local clock, right? So you receive the data, then the query processor, what it does is, in this case, because it's a read statement, read transaction, the query processor will look for the shard map of the storage where the data is being stored on the storage layer, and you go to the read path, you go directly to the storage. It doesn't need to go through any adjudicator, any journal. You go to the storage, and then you return, look here, you return the data back to the query processor, and the query processor will return the data to the front end, return the data to the client. Now, these results, of course, will be merged here and will be sent to the customer. There you go, and you see the specific pizza place that you have. Let's look at more complex query where maybe the user does not only want to run a simple select transaction, but also wants to do some interactive transaction, potentially inserting data into the database. So the query, of course, you're going to create a transaction, in this case, select, restaurants we rate 4. I actually want to see a specific restaurant ID, and I want to say specific item, right? So you're selecting the item. Then you're saying, I want to order this item, which is a pizza, and then put this pizza into my order table. So you selected the restaurant, you chose the item you want, and you placed the order. Let's look at how these actually work behind the scenes with the SQL. So again, what we're going to do here is we're going to have a transaction T time using Amazon Time Sync, right? What is going to happen here is the query processor will get a snapshot of the data from that T time, the start time, the T start, right? That snapshot is going to be loading to the query processor, and then every single read and every single write will only be done within that specific query processor. It's not touching the storage yet. It's using optimistic locking, which allows for concurrent writes to be done at the same time if they're not actually using the same rows. So in this SQL, the query processor acts as holding tank for all these statements, waiting for a commit statement before it sends the full transaction to adjudicators to be checked. We'll talk a little bit about what the adjudicator does in a moment, right? Think about the query processes being displaced here. Now, the cool thing about how this works, right, is once you have a start of the transaction, you have that key time, you have the cross-region transactions proceed very similar to a single region transaction. The read path is barely changed, so you can just grab the data from the storage nodes that have the shards. Now, when you do the select, insert, and update, no cross-region interactions are required here because the optimistic locking that DSQL implements. So the way this works is the latency is only incurred at the commit time. So on the query processors, you're going to go through, you're going to do select, you're going to do insert, and you're going to do update. And once you finally have your snapshot with all the commitments, with all the data that needs to be commit, it sends to the adjudicator, and we're going to talk about the adjudicator in a moment, but it's sent to adjudicator, and the goal of the adjudicator is to go across both regions that you have and make sure that after your T start, that no other data has been transacted into your storage and your journal that will conflict with your specific request. If there is, only one of them is going to be committed and the other one's going to be aborted and you need to retry. But if not, the commit is when you incur the latency. So you're not then incurring the latency into every single select, insert, and update. That is not how it works. You only get the latency when you're doing the commit cross regions. This means that reads, writes, and updates are just as fast as they would be in a single region database. Only the commit part is where you incur the cross-region latency. And the cross-region latency could go between 15 to 100 plus milliseconds, depending how far each region that you have linked together are from each other. If they're close to each other into the US, they're going to be a little bit faster, between 20 to 30 to 40 milliseconds. If they're far apart, it could be hundreds of plus milliseconds at the commit time, because speed of flight is something that we cannot expedite, at least for the time being. So let's talk a little bit about the query processor, because there is a lot of innovation that has been created behind the scenes. So as you've seen, the query processor is doing a lot of work. Is the heart or where the SQL architecture runs? It runs inside what we call a firecracker virtual machine, micro virtual machine, which is where the query processor hosts within a server, in this case, a bare metal instance, right? A firecracker micro VM was created and built for Lambda in 2018. And this is the same technology that the SQL query processors is using behind the scenes. It's an open source micro VM that AWS has open source, and we've used to put a secure box around the Postgres engine. So Postgres will be running on top of this query processor, which is a micro VM. So the cool thing about this is, as your database grows in scale and demand, this can literally scale to little as tens or one query processor at any given time, or zero if you don't have any requests, to tens of millions of query processors being created. Each query is going to create a query processor. Like each transaction, is going to create a query processor. Another cool thing is the support of snapshot isolation. So in this SQL, we support an isolation level called snapshot isolation. So what does this actually mean? It means that each transaction operates on a consistent snapshot of the database as it exists at the start of the transaction. So as you do the write from the storage, and you see here on the right of the screen, when the snapshot is being created into the query processor, that snapshot isolation will only exist on the query processor. If you have any writes and updates and inserts, then you try to do the commit. If it's multi-region, use the adjudicator to make sure there is no conflict across the commits across different regions, right? So the transaction proceeds through the SQL execution phase where the reads see the consistent snapshot being put back into the micro VM. So when a write operation occurs, like an insert or update, they are not immediately applied to the storage. And that is a very important thing to think, right? Very different than other databases. and how databases are architected. If you would do a read or an update or an insert, you would be automatically done in storage. At this time, because we're using optimistic locking, what it does is it uses that snapshot that it got from your read path, and every time it has a write, like an update or an insert, you run that locally. Instead of, we spool these writes locally, and you create a private workspace for this transaction. What these approaches allows you to do is read your writes. So you don't need to subsequent reads within the same transaction that can see pending changes on the storage. That increases performance and scalability, which is one of the very incredible things that DSQL allows you to do. As you are doing these writes locally on your query processors, there is a challenge, right? What happens if there is another transaction that is trying to write at the same row that your existing transaction has? So let's say you have transaction A and transaction. You need to have a capability on your database engine that can look across these specific transactions and decide, is there a conflict or is there not a conflict? And that's what the adjudicator allows you to do. The job of the adjudicator is to detect and resolve conflict between transactions and ensure the writes are consistent, because you have a relational database, they need to be ACID, and by having that, they need to be consistent. So when you look at transaction A, for example, when you create a payload, you have a T-start. And remember, the T-start is the time when you're actually receiving the reads from the storage, right? Then you can do a write of sets, post images, that is the payload. You send the payload to the adjudicator. A payload will contain the write sets, which are the items that you modified, copies of the table rows applying effects of a transaction. The payload also contains the transaction start time, which is the T-start, which is a crucial element in committing or aborting the transaction. So let's look at how this works. So coordinate once only at commit. So you have your query processor. Once it's ready to, once the query processors have done all the transactions that has been given, what the query processor does is sends you the adjudicator and pretty much says to the adjudicator, dear adjudicator, here are the keys I intend to write, and here are my transaction start time. If no other transactions have been reading these keys since the start time that I've done my read, pick a time for a commit and write these changes to the journal, your friend query processors. What the adjudicator will do, you'll never allow another conflict transaction to pick a lower T commit, right? So if behind the scenes there was another transaction that comes few seconds after this and says, oh, I have actually a transaction that is started after the T start, but before the T commit, the adjudicator will be like, you are not going to be able to do that. It's going to abort your transaction and your application needs to retry the transaction. That is one of the things that you need to be aware as building applications with DSQL, that you need to retry if that transaction gets aborted by DSQL because there was a conflict. I'm going to show you in the multi-region active scenario that adjudicator is the piece that grows across the region, right? That is the piece that goes across the region. And it shards different keys across different regions, those two regions. So it needs to send the data for a specific query across the regions to make sure it's actually able to do that commit. So if you have two specific transactions that are changing the same row, right? So if I have transaction one that is started 10:09:33, but 10:09:35, if I have the two transactions, A and B, and they start roughly at the same time, but transaction A sends a commit for the transaction is likely before transaction B, what will happen in this case? In this case, what would happen is the adjudicator will look at, are you trying to write at the same row? In this case, adjudicator discovers intersecting writes, right? And so you compare the payloads from the query processor. It's looking for any writes that have a T start time and propose what needs to be indexed. In this case, as you can see here, it's trying to update the same payload. So only transaction A is going to be approved because both can change the same row at the same time. So transaction A is going to get committed, where our transaction B must be aborted and your application must retry, because then when your application retries, you actually go to the storage layer and retrieve the new data that transaction A has just updated, so you don't have any loss of data or any inconsistency. Now, the cool thing about Adjudicator is if the transactions do not intersect, in this case, you can see one of the, maybe it's too small for you to see, but transaction A is trying to write on item ID 3, and transaction B is trying to write item ID 7. Even though some of their selects are exactly the same, both transactions are going to be allowed to be committed, and both commits will proceed, which is really good. Another very interesting thing about the SQL is, in traditional databases, the durability happens on the storage layer. Transactions are only committed once they are durably written in the storage layer. That is for traditional database. So the storage layer is expected to be able to recover all committed transactions from storage after any failure. These requirements add significant complexity to the database engines, including logging, coordinating systems APIs, and need to keep a storage consistent with Mori for recovery purposes. On the SQL, the durability is given to the journal. And of course, the journal, if you're using a multi-region active solution, is replicated across multiple regions. And this is where, if you remember when I said I have the witness region, that witness region is a replication of the journal. Journal is just where all your transaction logs for your database are stored. So this SQL manages this complexity by making the journal responsible for the short-term durability. Transactions are considered committed once they are reading to the journal, not once they are reading to the storage. The journal can scale horizontally, and transactions can be reading to any journal. They coordinated to provide a totally ordered stream of committed transactions. Remember, because now the adjudicator makes sure that the priority and the order of the transactions are in place, the journal now have these transaction logs that are ordered. And the crossbar component uses the journal's ordering to ensure that the dates that are applied to the storage are in the correct sequence, even when there are multiple journals. So this is the cool thing, right? Because now you have this journal that can scale horizontally, and any transaction can be written to any journal. But because the ordering that Adjudicator allows you to do is the crossbar components reuse that journal ordering and ensure that the storage is also save the data into the correct order. And this is actually pretty cool. So the payload and the timestamp are sent to the journal. Once the journal acknowledges the write, the updates then are sent to the storage nodes. The journal sends a success code to the query processor, which sends back a success code to the client. From the user perspective, the transaction is done. And this is the interesting part, because now the journal is where the durability happens, right? And journal is the place that says, okay, it's good to go. You go, because it's replicated across multiple availability zones and multiple regions, and it has the consistency and the order that you have. So we talked a lot about this SQL so far, and I have a couple more slides before I end the presentation. Aurora DS SQL uses optimistic concurrency control. So rather than putting a lock when you are starting an insert and you need to do multiple selects and multiple inserts, multiple updates on the row, that is not how it works. Doing a pessimistic lock allows you to have a concurrence play here, which makes a crucial role for multiple transactions to occur simultaneously without leading to inconsistency of data. You might need to retry some of those transactions if the transactions are within the same period, as I explained the capability and the role of the adjudicator. There are no deadlocks. Conflicts will be detected at the transaction commit by the adjudicator. You have a multi-region concurrency protection now, because every single data that is committed is guaranteed, if you're using an active multi-region architecture, that they are consistent across these regions. Now we have an efficient storage layer for synchronous replication because of the journal capabilities, and allows you as a developer to really design new capabilities and new design patterns for developers. There are multiple things here that we could talk about it, but I'll show you some of the extra documentations that you can go and do a little bit of reading. There is great reinvent videos also posted on the AWS channel. What I want to show you is behind the scenes, how is the architecture for an active DSQL database? So when we look at an active architecture, you have three regions. Like I said, you have one region, two regions with endpoints, region A and region C in this diagram. And region B is what we call the witness region. You have one router on each of those regions that have endpoints. Those are the endpoints. And then even though it says one query processor here, one box, think about that being the micro VM from Firecracker, which is going to run the Postgres engine there. So you can have multiple query processors. Each actually transaction is a query processor invocation on its own. DSQL internally will actually host across multiple availability zones, right? So realistically, your stack could be duplicated across 3 availability zones in each of these 3 regions. And here you have the adjudicator, and you can see here the adjudicator is the only one that is responsible, the only one that requires you to have a cross-region communication at the commit of a write. And you can see that adjudicator will have specific keys that are led by specific adjudicator in this case, because that's how you guarantee the consistency across the transactions for multiple places, multiple regions. Then you have the journal, and you can see that the journal is actually replicated across all the 3 regions, because that's where the durability happens. So the journal is where the transaction logs are stored, and it's a critical key component of the SQL. Then you have the storage, of course, that will read from the journal. You have a crossbar that is not in this diagram that you read from the journal and actually make those changes into the storage. The journal only witness, which is region B, ensures that if there is a split between those 2 regions, the available side can continue to be available and consistent for client on the other side of the partition. For distributions that go across large geographies, you can put the witness kind in the middle, right? So if you have, let's say, one region in the US, and you might have another region in Australia, you might want to put another region maybe in the Middle East or in Europe, right? That is a nice sort of additional property that you can actually optimize for latency as well. So let's talk about what happened if region C in this case goes down. Let's knock on the wood here, but let's say if there is a catastrophe or something happens with the region C goes down, which is very uncommon, but let's say the region goes down. Any adjudicator leadership that short-lived state for doing an isolation moves out of their region C, and remain into the health region. Because remember, you need all the keys for the adjudicators to make the control. Now, the journal is split across region A and region B, which is region B is the witness. So you still have that durable storage in 2 regions. And only the health side of the database remains available. Of course, the endpoint on region C won't work, but endpoint on region A will continue to work for reads, writes at any given time. So you then need to move traffic to the health side of the partition. So you can just either use that specific endpoint, or you can do a Route 53 latency sensitive routing with health checks and so on. It's how you are using the endpoint on your application is completed for you. You can just have one specific endpoint for the region, or you can actually potentially just create a DNS with Route 53 that you do the routing with health checks for that specific regions that is worn. So this is what I wanted to present to you about DSQL. DSQL is currently in public preview. Hopefully soon it will be in general available, and that you will be able to run production workloads. But if you have interest, please feel free to reach out on LinkedIn. Again, my name is Samuel Baruffi. But also you can scan these QR codes. We have the documentation of DSQL, some of the DSQL public web pages, and also the useful blog posts that we share. And as mentioned, there are great reInvent 2024 talks that are available for you to consume on YouTube, and I highly recommend for you to do. So let us know what you thought about that. Hopefully you'll be building new, exciting, resilient, and highly available applications on top of DSQL. and we are very excited to see what you can do. So thank you so much for taking the time to watch my session, and I will see you